Okay, so I think it's currently recording.
Oh, good.
Shall we start?
Okay. Okay.
So yeah, that one there.
Determinants of small matrices, but it's combinatorially expensive unless your matrices are sparse. So applying it in a large problem requires reversal of perspective. Another of our favorite examples is finding eigenvalues by finding roots of polynomials. When you first take a numerical analysis class, you learn, in fact, eigenvalues are easy and roots of polynomials are hard. And having to unlearn that approach is important. So that's the framework of the course. I should tell you a little bit about what we actually did in the course. We presented students with sample vignettes and sample pieces of code, more scaffolding at the beginning than later on. We taught them to program in Maple in a very elementary way and gave them programs and asked them to do experiments. And one of the first things that we started on was simple continued fractions. These are accessible and not in the standard curriculum. One of the things I didn't want to do was stomp on the standard curriculum or steal their thunder. I made a minor exception when we came to eigenvalues, but that's another story. So simple continued fractions. We also looked at Newton's method and fractals and Bohemian matrices, these kinds of things. Those are the ones that I'm going to look at, and then I will hand the microphone over to Eunice to talk about maybe the most interesting vignette, which is the chaos game representation. So I'll begin with a quote from Carl Old's book, Continued Fractions. Old's won the Chauvenet Prize for his paper, A Simple Continued Fraction of E, and I really recommend reading that paper to anybody who hasn't read that. So this is the way his book, Continued Fractions, opens. He says, at first, nothing seems simpler or less significant than writing a number, for example, 9/7 in the form 9/7 equals 1 plus 2 over 7, etc. And we demonstrate the algorithm for constructing the continued fraction of a rational number in this way. And I actually start with that quote. The students see that Old's saying that this seems simple and insignificant. The next thing I do is present them with a sequence of numbers, just out of thin air. I just write this sequence of numbers down. 1, 3 halves, 17 twelfths, 577 over 408. And later I go back and explain that this came from a particular iterative scheme. Xn plus 1 is xn plus 2 over xn divided by 2, which is, of course, Newton's method for finding the square root of 2. And then I, again, out of thin air, just note that the squares of this sequence can be written as 2 minus 1 over 1 squared, 2 plus 1 over 2 squared, 2 plus 1 over 12 squared, and 2 plus 1 over 408 squared. So if you look up that sequence on the online encyclopedia of integer sequences, which I showed them, the students really like that, then you get a full list of these numbers, and students get to see that this rule persists, so that the squares of these numbers rapidly approach 2. So these are square roots of approximately 2. And the connection between square roots of approximately 2 and approximate square roots of 2 is something that we actually work on. Then, of course, I expand these in simple continued fractions. And we get 1, 1 plus 1 over 2, 1 plus 1 over 2 plus 1 over 2 plus 1 over 2. And, of course, I'm using the shorthand notation for this. And the next one has 7 2's in it. And I get them to guess what the next iterate would have. And of course we have 2, 3, 7, and 15 2's in this, so they see that there's a very definite pattern in the increment of the number of 2's. And in this active learning framework, the students are really shy at the beginning. They're told they have control over the curriculum a little bit and control over what to do, and they're both excited about it and a little scared. So, okay, this is the simple first exercise. And then, of course, getting them to try to really say confidently that the square root of 2 really is equal to 1 plus 1 over 2 plus 1 over 2, where we go on to an infinite sequence of 2's, is actually really difficult. They don't want to do this for two reasons. One is they don't really know what convergence means, and the other is they know perfectly well that square root of 2 is irrational and doesn't have a pattern in its decimal expansion, and they're really surprised about it. It's part of my aim is to make them feel surprised and willing to experiment some more. I think as professional mathematicians, we're very used to feeling surprised when we run across something new. It's kind of what we live for. And you want to give that to the students as well. You want to give that in some real way. From there, move to Newton's method because I want to explain where that sequence comes from. And we actually wind up finding roots of various things via Newton's method. And I try to coax the students into asking the question, how do we start it? What initial guess do we use? And in fact, it's very easy to do that. That's a very common question for Newton's method. People just don't really know how to get it started. And then you say, well, let's try them all. And that's where we get the Newton fractals. And the students are very startled and surprised to see these crazy kinds of things in here. So the example on the screen is a Newton fractal for hyperbolic cosine plus 3 over square root of hyperbolic sine, which is actually Halley's method for hyperbolic cosine plus 3. And the connection between Newton's method and Halley's method is something that we get to play with. And there are other iterative methods that we play with as well. After you get the students to play around a little bit, they want to explore. And what we did was I wanted to have a competition. Here, find the most beautiful fractal. And the students didn't want to do that. They said, no, we'd rather have, just let's go and do lots of different ones. And so they chose a whole bunch of different functions on their own and made Newton fractals using Maple out of each of those. And I said, well, okay, do the same function both in Newton's method and with Halley's method, and look at the different basins of attraction. And they came up with all these examples, and Eunice made these posters out of the students' answers. And if anybody wants the details of those functions, we'll send that to you. Students really enjoyed that, and they enjoyed the fact that they were involved in producing something. So for Bohemian matrices, one of the later vignettes, they couldn't really generate the pictures in class time frame. It takes a little while for code to generate pictures like these. But on in the course of a course project, that worked very well. And I had several students do some very interesting projects based on Bohemian matrices. Some of the first pictures of circulant matrices were generated by an undergraduate student, and so on. So I really want to talk to you about Bohemian matrices, and I'm trying to bite my lips so that I won't. I'm just going to say, if you want to find out more about Bohemian matrices, there's a recorded talk linked under bohemianmatrices.com. And we can just look at one more of the pictures from there. We'll look at what my student Stephen Thornton calls eigenfish. I turned this one on its side. I think we actually have space alien visitors here. This is actually a two-parameter family of matrices, and you let the two parameters vary, and you generate algebraic surface. You project the algebraic surface, you get some very interesting shapes out of that. So they're waving at you from London, Ontario here. Now I'm done my part. Tag. You can have the big chart.
So, hi guys. So, just to introduce myself a little bit, I am Rob Corliss's PhD student. For this course, the first time the course was run, I was a student, and then for the second time I was the TA. And therefore we got the idea to create an online book for future references, I guess. So what I'm going to be working or talking to you about is chaos game representation. So how we introduce this topic to the students is through the chaos game. So here you see we have 3 points, and sorry, did anyone say anything? Oh, okay. So we have 3 points, and each of the points are labeled. So the top one is labeled 1, 2, the bottom left one is labeled 5, 6, and the bottom right one is labeled 3, 4. So let's just pick a point and let's just call that the starting point. Typically, we set the starting point in the middle of the triangle, but for aesthetics purposes, I just like choosing the top point. And of course, we're not going to have a die on hand or a dice on hand. So, but everyone has a phone, so we can just log on to random.org and use their dice roller. And I rolled the dice digitally, I guess, and we got 6. So what we're going to do from our pre-existing point, we are going to draw an imaginary line to the point and then draw a dot in the middle of that line. It looked frozen.
You look frozen, but I hope we are not frozen.
You are not frozen.
Okay,
Okay,
perfect.
good.
All right, so we can do this again. If we roll the die again and we get 4, we can take the previous point that we had just plotted and draw an imaginary line to the dot that is labeled 3, 4, and put a dot in the middle of that imaginary line. We're not going to do this by hand over and over again. We can use a computer, and if we do this 100,000 times, we get something that looks like this, which is something familiar to most students, and therefore we think is a good starting point for them to get interested in chaos game representation. So we also look into what if we have more than 3 points. So there's the square and pentagon, so on and so forth. And we also varied the placement of the points. So previously we put the dot in the halfway point of the 2 dots, but we can vary it and put it a quarter of the way or like 9/10 of a way. So we vary different parameters to entertain the students in a way and get them more interested and get them to code more and be more comfortable coding. There's another way of generating fractals, which is something called iterated function systems. I'm not going to go too much into it, but it is something to connect these pictures to a mathematical equation. So here we're using linear algebra, and since these students are typically in first year or our target audience is actually high school, introducing linear algebra this way is actually one way of them being more interested in mathematics, and we want to put a connection there. So using these, we can create the Barnsley fern, and we can see that it resembles the black spleenworth, which is what it was intended to do. So many students are very interested in these pretty pictures. And
hello, Michael, if you're there.
yes, hi. And so this is the main meat of CGR. So what we're actually interested is using CGR and plotting gene structures or DNA sequences. So what we're going to do is place the 4 bases, adenine, guanine, cytosine, and either thymine or uracil, depending on whether you are plotting the DNA or mRNA. So for example, here we have a sequence called human beta globin. Regardless of the sequence, we're just going to take the first few and show you how you would go about using CGR. So let's just look at the first 5. So we can see here on the bottom left corner we have A, and then you move up C, G, and U. In this case it's actually T, but that's fine. And our initial point is in the center here. And the first base in our sequence is G. So like before, from the previous point, which is our center point, we draw an imaginary line to the top right corner, which is labeled G, and put a dot in the center or in the halfway point between the 2 points. And we can repeat this for the rest of the bases. And if we do this for the whole sequence, we end up getting this picture. So this picture actually tells us quite a bit about the sequence itself. And you can see these patterns recurring. So these are what we call double scoops. And what this signifies is that the C base, so cytosine and guanine base, are never one after the other. and is due to some chemical structures of these bases. Some biologists in the audience possibly could tell the audience why this is, but I'm not a biologist, so I'm not going to go into that much detail. But that's why there's a double scoop pattern here in this picture. So let's move on and take the CGR for other DNA sequences of some species. So in this case, we're taking the mitochondrial DNA because it gives you a snapshot of the whole entire DNA without that many base pairs in this sequence. So usually we're looking at sequences that are around 16,000 base pairs in length, which isn't that much, but at least we get some sort of image from these bases. If we get too many base pairs, then the image ends up being too black, and we actually can't distinguish any image or pattern. So usually around 16,000 is a good amount to see some sort of pattern. So without telling you what species these CGRs represent, we can automatically see that the top two look pretty similar, or more similar than the bottom two. And if I reveal to you what the sequence or the species are, you will understand possibly why this is. So let me reveal to you what the species are. So these are corresponding to the position of the previous one. So the top two are pretty similar. So the top left one is actually Homo sapien, which are regular humans, the modern human. And on the top right, we have Neanderthals. And in the bottom here, we have a gray-red horse. And on the bottom right, we have a groundhog seahorse. So we can see that we have different species, and we are able to tell them apart using CGR. But we don't want to just say, oh, these are different. We want to quantify these differences. So we use something called structural similarity index. And it takes the two images, and it is based on three terms. So one is the luminance and distortion, the second one is contrast distortion, and the other one, or the last one, is linear correlation. And similarly to the human visual system. So what we see in terms of differences are luminance and contrast and so on and so forth, and therefore they were basing this calculation on this. So here is the equation. I'm not going to go too much into it, but you can see that we have some terms for the luminance and contrast and so on and so forth. However, in this case, we want to take the dissimilarity index, and that is because we want to map the distance between the two species, meaning that we need to find their differences. What this is simply 1 minus the similarity index. And just a note, if the dissimilarity index is equal to 0, it means that the images are equal or identical. Whereas if the dissimilarity index is equal to 1, then they are complete opposites. So for example, one image is white and the other one is completely black. So going back to our 4 species, we can calculate our dissimilarity index. And here are some numbers. I'm not going to go through any of them. I just want to point out that the dissimilarity index for A and B, which represents human and Neanderthal, is very low, whereas everything else is pretty close to 1 or very high, meaning that they are very different from one another. Using this information, we can put it in a dissimilarity matrix. So each of these represents a species. So we can say each column, the first column is human, second column is Neanderthal, so on and so forth. And the first row is human, second row is Neanderthals, and so on and so forth. So we're taking the relations and putting them in the corresponding spots. Then we can map these distances on a Euclidean plane. In this image, I have plotted around 700 species and took the distance between them. One thing that I wanted to point out is these 3 points over here. So these points are purple, which represents lungfish. So whenever you think of fish, you don't think that they have lungs, but apparently there are at least 3 species known where fish has lungs. And look at where it's placed. So we can see that yellow represents bony fish, green represents cartilage fish, and red represents amphibians. So we can see that the lungfish is somewhere in between amphibians and bony fish, which kind of makes sense to us intuitively because it's some sort of hybrid, I'm guessing. We can also apply CGR to mathematical sequences. As Rob said earlier, we introduced the OEIS to the students, and here's just a screenshot of what it looks like. And using continued fractions, also Rob introduced that earlier in this talk, we can use CGR. So I'm not going to go too much into detail, but for example, for figure A, we have the partial quotient for the continued fraction of square root 2 mod 4. We can see it's not too interesting because all of the partial quotients are equal to 2, and therefore it keeps going up to that corner. And you can see some sort of, I guess, uninteresting characteristics in B, and a little bit more interesting characteristics in the last figure. So that's all I have to say. And thank you for listening to our talk, and thank you for having us all the way in Canada.
Yes, thank you very much. We're ready to take questions.
Seems obvious. Questions? I will bring the mic to you.
Hi, Rob. Here's to ask a question. So, would you mind to explain a little bit about the Jupyter project? What is a Jupyter project about?
I'm sorry, but I cannot understand you.
I'll repeat Besso's question more slowly if I can. Beslin Youngik, whom you know, Fraser University, wants to know more about the Jupyter project, please. Can you tell us more about the Jupyter project?
Okay. Do you want to answer that? Tell them a little bit about Jupyter.
Okay, so Jupyter Notebooks is an interface in which you can play around with code, and it has a markdown component, so you can pretty much incorporate text, which kind of describes your code, and code in the bottom, which allows students to play around with pre-existing code, or they can code by themselves, certain problems that you may introduce. We picked Jupyter in particular because number 1 is free, and number 2, we think Python is quite a good language to start with. Anything to add?
Can't think of it, except the Blackboard attracted us. Otherwise, you would have got a demonstration of Jupyter Notebook.
Great, thanks. I have a little question of my own, if I may. As you might know, I've just started my YouTube.
I'm sorry, Judy Ann, but your voice is breaking up, and I think the connection is bad, and I have bad speakers here. Rather than try to frustrate everybody here, we'll just take questions by email. Just send us your questions, and we'll answer. And it doesn't have to be done real time.
That would be fun, though.
It would be fun.
I'll ask one more quick question, if I may, and we'll just see how we go. And otherwise, we'll close off and we'll take a suggestion about email. My question is, in the Australian curriculum, there is a requirement for ICT, for computation. And looking
Now we
at...
can hear you.
Can you hear me?
Now we can hear you.
It's much better now, so
Excellent,
if you don't mind
So
repeating
in
what
the Australian curriculum, there's a requirement for computation, and it's often not actually done in maths classes. And looking at how university maths people might contribute to school classes, would it be feasible for university mathematicians to come up with little computational projects or tasks which link in with the school curriculum, do you think? Might that be a productive interplay that we could try?
If I understand your question correctly, yes, it would be productive. There are many areas of mathematics, not just the ones that we picked, where there are computational questions that that lead into some very interesting and even open questions. So Neil Calkin was giving many examples when I last talked to him about the various sequences that can be generated. There are many graph theoretic questions, and some of these lovely computational questions are easy to say and really hard to solve, as you know. So yes, there's plenty of room for adding. And in the notebook framework, that's explicitly what we wanted, was to encourage other people to contribute new problems, new vignettes, new explorations. And so yes, we do want to make it open in that sense.
Yes. Let's continue that conversation by email. Does anybody
Yes.
in the room have a question at the moment? What do you want to say that for you? Looks like people are just full of thoughts and they'll need some time to compose those emails to you. So get ready for a flurry of emails. Thank you. Let's thank you again.
Thank you for listening. Thank you for being there. Thank you for the invitation.
Thank you.
Bye.